Suppose you have comes from some finite distribution with some mean, some finite variance. I, of course, is 1, 2, 3, dot, 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 up to n. What would the joint distribution of two random variables be? Well, joint distribution simply means that x and y, or x1 and x2, occur simultaneously at the same time. Think about multiplication probability. What is the probability of A and B if A, B are independent events? Probability of A times the probability of B. Same logic, because when we're talking about probability density, we're just talking about probabilities of multiple values, right? If you pick for a single value, we can't with the normal distribution. You know, we did that delta, dx part, wrote it as, we had to look at it, look in a very small interval. But if we hypothetically look at that small interval, we can extend the idea of a multiplication of two densities. So the joint density of two random variables is simply the product of their individual densities. If I have n random variables, all n of them, and each taking some xn, what would that equal to?
Well, we know that they're always independent.
Mm-hmm.
How do we know that?
IID.
Oh, yeah.
Independent.
They told you so. It's the product.
Now, of course, I don't need the x1, x2 hard, right? The reason why we put the x1, x2 is because these values need to be the same. In other words, I can't simply write it as fx times fx and call it f of x, f of x times f of x, call it f of x. Won't make any sense because we're not using the same x always. Maybe once we would, but this x1, this value there, and that value there, they didn't be the same. So we pretty much end up having n-dimensional space. Good. Now we want to extend the idea to ordered statistics. Let's just start with a simple case. We have two random variables, x1, x2, and we want to find their joint distribution. So we have two ordered statistics, right? X1 and x2. They have regular x1, regular x2. the first possibility is x1 could equal that, and x2 will be that. Possible 1, 2, 3.
I don't follow.
So. Suppose you draw two numbers from, say, a normal distribution with mean for standard deviation 2. So you get x1 to be 2, x2 to be 4. Okay. Now, what would x1 be?
That would also be 2.
That would also be 2. x2 would also be 4.
Right.
Yes, but that were to be 2. Excuse me, 4, and this were to be 2. What would the order statistic be? The minimum would actually be
X2.
x2, which is 2.
So is the general form divide by factorial?
So divide or multiply. So if you have two of them, you've got x1, x2.
But I'm thinking of like all the combinations.
All
of all factorials.
orderings, all orderings.
We only want one of the factorial combination, right?
No, we want all possible orderings of, bunch values for x1, x2, all the way up to xn. All possible orderings. But what are all the possible orderings that you could have? Well, how many orderings are possible? N factorial.
Mhm.
So have n factorial times f x1 of x1, x2.
Okay.
Wait, what's, oh, you just ran out of room.
No, I'm just trying to write it on the slide. I'm not introducing a new concept here. So if we extend it for n ordered statistics, this would simply be n factorial. Oh, that should be 2. And you can say that a joint distribution in and of itself is challenging, especially if you have to move on two random variables. Because two random variables, you end up in 3 dimensions if you want to plot the density. And higher dimensional random variables will only make things more complicated. So if it is going to be hard here, just as hard over there. Certainly we're just multiplying it by n factorial. But if I want to find a joint distribution of the second and the third order statistic, what would you do? Would you put 3 factorial here? Or would it still be 2 factorial?
Ask the question again.
Second and the third order statistic. Joint distribution of the second and the third. Would it still be 2 factorial? It'll still be 2 factorial because you still have 2 items, right, to order. So x2, x3, x3, x2. So it doesn't matter how many, it does matter as to how many observations you pick. But what doesn't matter is the index, which one you pick. It could be 1, 2, 3, 5, and 7. 5 and 7 would still have 2 factorial f. Yes.
So the latter one is a more specific order, right? For first, second, and third, all the way through n. It just seems like if we were looking at like what's the probability of x1 being first, x2 being second, and x3 being third, But that would change the factorial, but you're saying it doesn't.
No. Say if you have 2, 4 with 2, right? Let's say you have another variable x3 from the same distribution. So you get 2, 4, 1. So one orderand would be 2, 4, 1. Another orderand would be 1. How many orderings do you have? 6 of them, right? You have 6 orderings, but all 6 orderings would follow the condition. Do you agree?
What do you mean by condition?
You can multiply them individually,
Okay.
right? All 6 of them will follow the same thing. Reason being they are independent, identically distributed. Yes. So all we're doing here, we're getting this n factorial times this because of the fact the first ordering would be that. Second ordering would be that. Third ordering, the same. So you have how many possible permutations or orderings? N factorial. So add them all together, you get n factorial times. Good.